Flow measurement based on pressure drop is the most commonly used technique in the process industry. So let's see how this measuring technique works. A plate having a center orifice, as seen here, is introduced in the pipe. The velocity of the fluid increases when flowing through the orifice. Therefore, the static pressure will vary as follows. The graph that you can see here shows the evolution of the static pressure across the pipe. Static pressure increases slightly at the orifice inlet, since the velocity in the dead zone that you can see here is almost zero. Then the static pressure decreases rapidly during the orifice cross, since the velocity increases. The minimum for the static pressure is observed just after the orifice. Then the static pressure increases as far as the velocity decreases, and the final static pressure is not as high as the initial one because of frictions due to the orifice. Now note here that a local vacuum could be generated around the orifice in the dead zones, especially in case of a low initial pressure and a high flow rate. In case of even a small tightness failure, air enters into the pipe, which represents a safety issue. The static pressure difference measured between both sides of the orifice is then converted into flow rate using the following formula, where F is the flow rate of the fluid, delta P is the static pressure decrease when crossing the orifice, and K is a flow coefficient. The precision of this flow meter is bad for low rates, since the variation low, as you can see here, is quadratic. Therefore, the orifice should not be designed for a very high rate compared to the nominal one. The flow coefficient K depends on the following parameters: the unit system used for the flow rate and for delta P, the geometrical characteristics of the pipe and the orifice plate, the fluid type, its viscosity, its density and its physical state, and the pressure and temperature. In general, this flow meter is calibrated using a reference fluid and at a reference temperature and pressure. The quality of the product and the operating conditions vary during operation and are different from the reference conditions. Therefore, it is necessary to introduce a correction factor to the flow coefficient K. Now, several devices based on this principle are used in the process industry. In refineries, petrochemicals, and chemical plants, you will find extensively orifice flow meters using an orifice plate, nozzle flow meters, and Venturi tubes. Let's take a look at the following 3D animation to understand how these flow meters work. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and the speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure difference in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate are essentially identical. And as soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chamber of the sensor. A higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure of the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effect such as excessive pressure loss or abrasion of components due to solid carried in the fluid. This demonstration shows that a sudden restriction generates severe turbulence in the fluid. Nozzles with a rounded funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluid with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles and finally with Venturi tubes, where the restriction is created by longer conical restriction in the pipe wall. All these designs can be supplied with different diameters and sizes so that the pressure loss and the differential pressure generated can be optimized for the process conditions. With this measuring principle, all liquids, gases or steam can be measured even at extremely high process pressures and temperatures.